The big races, like the Tour de France, show the size of the commercial market. The professional riders may be doing the pedalling, but it's the sponsors and bike manufacturers who are in the race. After all, what better way to sell bikes than by association with winning?
This is the image that permeates the sports bicycle market. We bought these clothes this morning from a local shop, and their advertising logos show how the amateur rider identifies with the professional racing scene. This bike also is a respectable racing machine, and it too carries its badge of identity. This effect is not limited to the sporting market. It stretches right down to the young person who goes with their parents into the local shop to purchase a bicycle. To the extent that that bike might carry no mudguards at all, or just vestigial mudguards. Highly irrational in this country. Now we're going to look at how two different manufacturers dance to this particular marketing tune.
The first manufacturer is in the mass market. Some 60,000 bikes a year come out of this factory in Pontypool, owned by Halfords. Of these 60,000, over 3/4 are sports models. Because it's a mass production factory, the emphasis is on efficient, cost-effective routes of manufacture. Components such as gears, brakes, pedals and wheel rims are all bought in. But the company does make its own frames, and the frame is what we'll concentrate on. Marketing manager David Duffield showed off the top-of-the-range sports bike.
We sell this machine for £120, and the other extreme, we have a machine which we sell for £80. We mainly have a basic frame set on which we bolt different parts.
Yes.
For instance, this one, being the top of the range, has got things like centre pull brakes. It has a 5-pin detachable chain set. It's a 10-speed machine. It's got aluminium pedals with toe clips and straps, and a very nice soft saddle with foam rubber and a cover of suede. So these are the things that the expert looks for. But at the far end, the young lad will be satisfied with a bike with steel equipment, which we can save money, and we can produce one for a low price. We have evolved over the last 3 years a frame set which is of 72-degree parallel angles.
Which angles are those?
Well, the angles are here. They've got the head angle of 72 degrees and the seat angle here of 72 degrees, which gives you a parallel angle.
That's an important part of the design strategy. Because the front and back tubes are parallel, two of the tubes stay the same size no matter how large the frame. So standardizing the length is important. But did they also standardise on cross-section and gauge?
No, they vary quite considerably. The top tube is 1 inch outside diameter, and that's a 20-gauge tube. The seat tube is also 20 gauge and 1 inch outside diameter, but the down tube is very important in strength, and that is an 18-gauge tube, and that's 1 1/8 inch in outside diameter. It's built that way because it has to stand a lot of stress and strain coming up from the front fork through the braking loads and down into the bottom brackets. It's a very important tube, that down tube.
The mild steel seam-welded tubes that will make up the frame are bought in cut to size. The ends are then mitered so that the tubes will form the correct angle when they butt together to make the frame. Small accessories, like pump pegs and cable clips, are electrically welded to the tubes. Spirals of brass, known as preforms, are inserted into the tubes for the later brazing operation. The frame is assembled from lugs and tubes. The correct set of components had already been selected for that day's production of bikes. The lugs are bought in as mild steel fabrications. At this stage, only the basic diamond shape is assembled. The tubes are tack brazed to the lugs using pure copper. This is just to hold the frame in shape once it has left the jig. Previously, the frame was drilled and pegged to hold it together, but that process was longer and more expensive than tack brazing. The remaining preforms are added and the joints are then fluxed. The frame is then hung over a timed gas jet, where this joint is heated for approximately 2 minutes. When the temperature reaches around 950 degrees, the brass inserts melt and the brass rises by capillary action to fill the joint. But at this temperature, the copper tack weld is still solid, and so that holds the frame together. The amount of brass in the insert is critical. Too little, and the joint is a poor one. Too much leads to costly finishing and cleaning on the frame. To speed handling, the joint is quenched after rough cleaning. The next operation is by hand. The rear bracket of the frame is brazed on. Frame assembly is completed by a further timed process on the bottom bracket. Because of the temperatures involved in the brazing operations and quenching process during fabrication, some distortion of the frame is inevitable. This is rectified by cold setting, which simply involves local yielding. That's not a problem, as it just means more cold work in the material. After minor machining, excess brass is removed from the edges of the lugs before the frame goes to the paint shop. So the manufacture is labour intensive, but the market pressure is to produce at the lowest price. David Henstone, Works Manager, detailed the component costs.
The lugs we buy in as a set, and they can vary from 90 pence down to 60 pence a set for the three. The bottom bracket at round about 90 pence. The manipulated tubing, nearly £2 worth of manipulated tubing and £1 worth of straight tubing. The total cost with the fork, we're around about £6.50.
And what does labour contribute to that?
Well, the labour element in the frame is approximately £1.50 on top of the £6.50. So we're talking a total cost of £8 for this particular sort of frame.
As you'd expect, the mass-produced product is designed for manufacturing efficiency. Parallel tubes simplify stock control problems, and mild steel really is a lovely material. You can weld it, braze it and quench it, and only affect the yield stress slightly. Like any structure, this one is a compromise between strength, stiffness and weight. And the advent of low-alloy cold-drawn tubing led to an opening for the craftsman's product.
This too is a bike factory. It's in a small village to the north of Whitby, where John Connell designs and builds bikes. John caters for the specialist market in lightweight cycles. Each design is made to measure for the individual customer.
The important thing is that the centre of one's knee joint is over the pedal spindle when the crank's in the horizontal. The seat angle depends on the person's femur to lower leg length, and with females, normally their femur is longer than a male's, and therefore they tend to sit farther back on the frame. A male having a shorter femur tends to be farther forward on the frame.
I see, and you were saying the weight affects the size of tube that you build in. Can you explain that to me a little more?
Yes, the weight governs the frame tubing and the frame stiffness. And for heavy riders, we use 1922 gauge tubing for the down tube, 1922 gauge for the top tube, and 2124 tube for the seat tube.
And those two gauges, what do they refer to?
The butted section, that's 19 gauge for about that length. Then you've got 22 gauge, and then you've got 19 gauge again. And the same thing applies to the bottom tube. But on the seat tube, you've got a single butt. You've got 21 gauge about this far, and then the rest is plain 24 gauge.
The individual measurements are transferred to the drawing board.
Well, this is a particular frame that we designed for a customer, a road racing frame, and his seat angle, which depends on the lower leg to upper leg ratio, came out at 75 degrees, and this angle normally varies between 72 to 76 degrees. The 76 degrees being used for somebody with a very short femur, the 72 with a longer femur, and the head angle, which is unusual on this road racing frame, was 72 degrees with a larger offset. I assume that he wanted better road shock absorption, and that's why he had this shallow angle with the bigger offset. This angle normally varies between 72, or 70 degrees actually, and 74 degrees. We file the lugs up very carefully and change their shape. You can only buy the lugs in one angle, or perhaps two angles. And of course you can see from the drawings that this doesn't suit us, and therefore we have to change the angles on the lugs. We're mitering the tubes so that we get this very accurate fit up between the butted joints, and the accurate fit up is important.
The frame is assembled on an adjustable jig, which John himself designed.
Now each of these arms is movable about the bottom bracket, and the scales, angles are measured, so that from the drawing that I do and from the sheet that we send to the customer, we can build up a frame on this jig exactly the way I've drawn it out. And then normally we have to set the lugs and also set the bottom bracket angles. When all that's done, the frame's put together, it's fluxed, and then it's brazed up on the jig, tack brazed on the jig. We're using silver brazing alloy, which is a very low melting point. It has a melting point of a range between 600 and 690 degrees centigrade, which is quite a lot lower than the brass. It has a very low heat input, and we have a very small heat affected zone. On the seat lug, we're using brass, which melts at a much higher temperature. The advantages are that it's cheaper, much cheaper than silver, and often when we're putting on something like a seat lug boss, it requires quite a lot of filling. Well, I think the man-hours probably in finishing the frame off must be about 4 or 5 hours for filing all the lugs and filing round all the extra braze-ons. Because it depends on how complicated the frame. The road racing frame has hardly any braze-ons on. The touring frames have an awful lot of extra braze-ons on.
Lower temperatures and slower manufacturing time mean no cold setting is now required. John manufactures in thin-walled tubing, which may cause problems.
Stiffness is our major concern, but strength also has a bearing on it. We're building in lightweight tubing, and as such, the stresses are high in the tubing, and we have to use a low alloy, high tensile steel tube.
It's on climbs like these that the out-of-plane stiffness of the frame becomes important. Energy which might otherwise be spent propelling the bicycle forward is used to uselessly deform the frame. A flexible frame might also exhibit nasty low-frequency resonances, which can affect the steering. I suspect that the front forks acting as a cantilever might be a major contributor to the out-of-plane stiffness of the frame, but John Connell disagrees.
Well, I don't think it's a major contributing factor. I think the whole frame itself moves, the rear triangle and the main frame itself, the main triangle, and we can increase the tube thickness of the main frame, but also on the front forks we've got a pair of front forks here. We've got the new Continental oval blades here and the standard fork blades that we use. Now these blades here are a thinner section material than these, but to compensate that they've increased the segmented area of this tube as respect to that tube. So one can use these fork blades on a lightweight frame set.
I see. Having decided that you might want a thicker wall tubing for the main triangle, do you do any comparative tests on your frames?
Well, we built this very big frame for a Norwegian, and we wanted to see what factors adding on extra tubes would make, and we built a rig and did some tests on this rig. We held the head tube on the milling machine between two blocks we produced.
Uh-huh.
The rear wheel was supported on a stand, and then the bottom bracket was loaded in the vertical plane with a spring balance and taking the deflections using a micrometer dial gauge.
I see. How does that simulate real-life riding conditions then?
Well, it doesn't really simulate them, but we want to do a comparative test, and as we added in on the various extra members on the frame set, we can compare how the stiffness increased with these extra members that we put in.
I see. What members did you put in, and how did the stiffness vary as a result of those members?
Well, we put an extra down tube in first,
Mm-hmm.
and we measured the stiffness, and then we added on 2 extra seat stays and measured the stiffness then. And with an overall increase in weight of 15%, we got an increase in stiffness of 30%, which we were quite pleased about.
Having gone through your production system, John, how do the material and labour costs of your frame compare?
Well, the material costs are about £19 for the tube set, about £13 for the lugs, bottom bracket, dropouts, etc. If we use the expensive investment castings, that's £28, which is considerably more. The frames take about 31 hours to produce, and if you take my time in the designing and my wife's time in the painting, it brings it up to about 35 hours, which is quite a lot for one frame set.
And what do you think you're offering to the market having completed this?
Well, I think we're trying to offer something which is, well, as nigh on perfect as we can, if you like.
Well, to bring these two approaches together, the mild steel frame is perhaps a little heavy, but it's certainly stiff enough. The low alloy steel frame, on the other hand, is lighter, but is maybe getting a little bit too flexible. Herbert Simon coined the word satisficing to represent these different designs. Both extremes and anywhere in the middle represent reasonable design solutions. You pays your money and you takes your choice.